So our first application is finding tangent lines and also equations of normal lines. That's where we'll spend more of our time today. If I'm finding the equation of the tangent line to this curve when x is 2, all right, one of the things you've got to make sure you understand or remember is that the derivative gives you what in relation to our tangent line? The slope, okay? So, we're finding the derivative. What's dy dx? Okay, yeah, you've got the 1 and you've got the minus 4x. That's 0, okay? So, when x equals 2,
-7.
okay, yeah. When x is 2, you could call this f prime of 2. We have 1 minus 8 is -7. So I know that's going to be the slope of my tangent line, okay? The slope of my tangent line, okay? Now, at this point, you just need to think, how do I find the equation of a line? I need a slope and I need a point. Okay, what point are we going to use?
2, 0. 0, 2. No, 2, 0.
2. How'd you get 0?
Oh no, you plug it in, so not 0.
Yeah, plug it in. So I want to use the point 2. Now, am I going to plug it into here or here?
The original.
The original equation, because I want a point. I already plugged it in here to get my slope. Okay, so I'm going to plug it in. Back in here, so I have 2 minus
8.
2 squared is 4 times 2 is 8, so 2 minus 8 is -6, plus 3 is -3. So now I know the slope, and I know a point, and I can find the equation of my line. Now, at this point, finding the equation of a line should be a piece of cake for you. So,
Is it the constant or not?
what do you mean?
What one is it?
The point is the point 2, 3. This is the point, you know, this is a parabola and it's going to look something like this, okay? The point 2, -3 is the point where our tangent line is going to touch. That's actually, you're finding the point of tangency, okay? So I could use my point slope form. Y minus a -3 equals the slope times x minus 2. And I simplify that. Okay, -7x plus 14 equals y plus 3. So y equals -7x plus 11. Okay, that's the tangent line to the curve when x is 2. Okay. Does that make sense?
I have a question.
What?
Where did you get the -3 from?
I plugged in 2. 2 minus 8
on the
plus
original.
3. In the original, yeah. Because you want a location on the graph.
Okay, because I plugged it in on the other thing. And
Yeah.
then I got the slope.
And you get -7 again.
Yeah.
That's a real common mistake, so be careful with that. That's one thing you guys have to keep straight. Am I looking for a rate of change? Am I looking for a slope? Then you're going to plug it into the derivative. If you're looking for a location, you need to plug it into the original function. Okay?
And regarding like procedure, is it alright if you just you put in the y, you plug in the y and the x, and you solve for b?
Oh yeah,
That works
yeah.
too? Okay.
How you get the equation of line is, as long as it's valid, I mean, it doesn't matter.
Alright, just want to make sure about that. I got the
Yeah.
same thing, but I don't
Yeah.
know.
And actually, this is a nice thing too. When we're getting into applications like this, how far you simplify your derivative really doesn't matter. Okay? For example, for part B here, if I'm doing dy dx, that's x to the 1/2, so I have a derivative of 1/2 x to -1/2. I can just leave it like that. Okay, I'm going to simplify the point of this problem is not getting the derivative. The point is getting the equation of that tangent line. Okay, so I can leave that like that because now I'm going to find f prime of 4. Now obviously I need to be able to interpret what 4 to the negative 1/2 power is. What is 4 to the negative 1/2?
Oh.
4 to the 1/2 is
Yes.
2, so negative 1/2 would be, no, not negative 2, 1 over 2, okay? So our slope here is 1/4, okay? So now I know my slope is 1/4. I know the point. The point is the point 4 something, okay? Well, what is it? 4.
It's 4-3.
4, 3, okay?
Wait, why is it 4 something?
Well, because I want to add
Oh, okay.
x equals 4. So square root of 4 plus 1, that's going to give me 4, 3. And then again, however you, now that you have the slope and a point, however you decide to get the equation of the line is up to you. I'll use point slope form again. And I get y equal to 1/4 x. That's minus 1 plus a 3, that's going to be a plus 2. So there's my tangent line. Okay? So we've done a little bit of that before. We didn't do a ton of it, but we did some of it. Now, why is that significant? Well, it's significant because now we know a path that would be tangent. So if we have this object, if this object is moving along this path here, and let's say whatever is keeping it on that path suddenly loses control, it's going to fly off on a tangent to that, okay? Or if we break whatever is holding this, like if you're orbiting around the moon, and you want to end up at Earth down here, you need to break off out of your orbit when the tangent line is pointing at the Earth. So you have enough fuel to get home. Okay? If you break out of your orbit and you're headed this direction, you're going to burn a whole lot of fuel, even if you have enough fuel to get pointed back in the right direction. Okay? They actually use these tangents to say, okay, this is when you need to leave orbit, and they will often slingshot themselves. They'll use that orbit to slingshot themselves out. They'll do it with satellites too. They're launching a new satellite. They'll have it orbit the Earth for a little bit, and then they'll shoot it out in the direction that they want it to be, and then wait for a few years till it gets to wherever it's supposed to go. But that tangent line, that's one application. Another thing is really the original application of the derivative was in relation to optics. Okay? Optics, the study of how lenses and things work. One of the key components of optics is that when you're reflecting light, okay, or reflecting anything really, you have a normal, okay? A normal is something that's perpendicular to the surface that you're going to reflect off of. And when you're doing a reflection, you hit the surface, and this angle right here is what's called the angle of incidence. Okay? You don't need to know these terms, but just to give you a background here. Well, one of the principles in optics is that the angle of incidence will equal the angle of reflection. Okay? So, in order to figure out how to do optics better, originally, and I forget if it was Newton or Leibniz, there were two guys, Isaac Newton and Wolfgang Leibniz, who both developed calculus for kind of different purposes. I can't remember which one did this application. But in order to study optics, they had to be able to figure out what this angle was. So they obviously needed to figure out what perpendicular to the surface would be. Except they were dealing with lenses. Well, how do I figure out what perpendicular to that is? You have to get a tangent, and then the normal will be perpendicular to the tangent. Okay? This is how the study of derivatives really came about. As they were looking, this was one of the problems that they were studying. Okay? Now, you hear that word perpendicular, and you're thinking about lines and equations of lines. What comes to mind?
Geometry.
Okay. What else?
Light.
90 degree
90 degrees. Okay. What?
slope.
Slope.
Oh.
We know the slope of the tangent line is
So there's
f prime of x. So what's the slope of our normal line going to be?
The inverse?
inverse.
Inverse.
Opposite. The
Opposite.
opposite.
The opposite inverse, or opposite reciprocal. So it's going to be negative 1 over f prime of x, right? Alright, so the normal line. The normal line is perpendicular to a curve at a given point. And the slope, or the gradient of that normal line at some point A, where x is A, is negative 1 over f prime of A. Okay. Now, here's the nice thing. We already did most of the work for this problem in our previous one, okay? I'll come right back, but this first one, we found that the slope of the tangent was -7, and the point of tangency was 2, -3. Okay? So we had 2, -3, and the slope of the tangent line, I'll put m sub t, equaled -7. Alright? Now notice they're using m sub n for normal line. So, what would the slope of our normal line be? Positive 1/7. Good. And now look, we already have the point from what we did previously. Now we know our slope, and it's the same process. Y minus a -3 equals 1/7 times x minus 2. The only difference is that we're using a different slope. Okay? So it's y plus 3 equals 1/7 x minus 2/7. We subtract 3, and y is a 1/7 x minus 3 2/7. And there's our normal line. Okay? Since we have a couple soccer players, here's another application of normal. Alright? A ball is circular. Okay? You gotta kick the ball, the majority of your impact has to be normal to the direction you want it to go. So if you want to take a shot and make the shot stay low, think about, okay, where is that direction going to be perpendicular? You got to hit perpendicular to the tangent, okay, that'll give you the direction you want, okay? If you hit perpendicular, if you hit at this spot here and the tangent is there, you're going to drive the ball straight into the ground, okay? If you kick the ball down here, here's the tangent, here's the normal, the ball's gonna go that way. Okay?
That makes sense.
When I actually learned that when I was playing soccer, that because everyone just says, well, keep your knee over the ball. The whole point of that is if you keep your knee over the ball, you'll kick it at a point where the tangent is going to have a normal that's aiming the direction you want, and you don't end up launching it sky high. Okay.
Any sport with a ball
I've
goes
done that
around the
once.
ball.
Yeah, anytime you're dealing with a round ball, if you're hitting a volleyball,
Then it's here going to the top, the same direction.
Yeah.
Same concept.
yeah, same concept.
Derek has
Okay.
seen me doing that.
What, the
it's
green
no
one?
void, yes.
I was the green one.
Yeah.
I put way too many shots over,
Oh yeah, I did that.
so I think everyone does.
Me?
If you ever feel bad, just watch the pros. They're not much better.
I almost scared him.
They launch them everywhere too. All right. So-
And then it went down. So it was even
Okay.
closer.
Try this one here.
And I
Try this
scored
one
my
here.
Olympic
We had
goal.
we had the point. What was the point? 4,
3.
3, and our slope was 1/4, right? So the slope of the tangent line was 1/4. Okay. So try getting your equation for the normal line there. See ya.
I'm a Jason.
Bye.
Have a good day. Afternoon. Wow. Adios.
See ya.
They're having fun. They sound like turkeys. I actually got a dolphin vibe from that. Really? I got a dolphin vibe. Turkeys probably. Well, one of them's coughing now.
I was thinking turkey. I was
Uh,
so, see ya. All right. So what's our slope for the normal line?
-4.
-4. Good. -4. Okay. That's the opposite reciprocal of 1/4. And then we have what for the equation of our line? What'd you end up with?
Y equals -4x minus 5.
Okay. So what you guys got?
I got plus 19.
You got plus 19. Anyone else get something?
Plus 19.
Plus
My bad.
19.
Plus
You lose a
19.
negative in there.
Yeah, that was my bad.
Okay. All right. So plus 19. All right. We have the again. If you use point slope form, y minus 3 is -4 times x minus 4. So you got a positive 16 plus the 3 to get your plus 19. All right. Does that make sense? Okay. All right. So the normal line, that's one application here of our derivative. Okay. Another one that's related to it that we've talked a lot about, and now we finally get to do it, is horizontal tangents. Okay. Why are the locations where we have horizontal tangents special? What are they going to give us? Or what we said? That's where it would be undefined.
Because that's when like it's the top point, like when it's
Okay. Yeah, like a peak or the highest or lowest points.
maximum.
Max and min points, alright? Now, that's typically the case. You will have cases that we'll look at in the future here where you'll solve for where there's a horizontal tangent, and in some cases it's possible for it to be what's called a saddle point or a plateau point. But we'll get to those. So for right now, we already said here for dy dx, on this one, we had 1 minus 4x, okay? Well, if I want horizontal tangents, that means I want the slope of the tangent line to equal 0.
So you set that equal to 0.
Yeah, so you set this equal to 0. Where is 1 minus 4x equal to 0? X equals
1/4.
1/4. Okay? So when x is 1/4, I know that that is going to be a horizontal tangent. Now, since this is a parabola, we recognize this. I know that's actually going to be where my, in this case, max point is. Okay? So here's 1. I know at 1/4, I know my vertex, my max point is going to be there on 1/4.
Will the slope of the horizontal tangent just be the opposite of the tangent, because in the first one it was -1/4?
Well, remember, this is not a slope.
Oh, it's just x.
The slope was 0, right? This is just the x coordinate when our tangent's horizontal.
Okay.
Okay? Now, when we plug that in, we can get a y coordinate, okay? Y equals 1/4 minus 1/4 squared is 1/16 times 2 would be 1/8. 2/16, which is 1/8, plus 3. That's 3 1/8. So guess what we now know? We know the horizontal tangent is up here at 3 1/8. And that means our vertex. Notice this actually helps us find our vertex. Our vertex is actually the point 1/4, 3 1/8. Okay?
Once you get the 1/4, you just plug it back in to the original, right?
Yeah. Because again, you're trying to find a location, right? So location, you always plug into the original function. Okay. By the way, a little connection here. What's the derivative?
2ax plus b.
Okay? And if I set that equal to 0, I subtract the b, right? I have 2ax, and x is
b over
negative b over 2a. You remember how we found the x coordinate of the vertex? We just memorized negative b over 2a. It comes from the derivative, set equal to 0. Okay? So. Okay. This one here, dy dx, what did we say that one was?
that was 1/2x negative 1/2.
Okay. So we need to get that equal to 0. So this is where actually simplifying that might be helpful. It's 1 over 2 root x equals 0. Okay? So question, when is 1 over 2 root x going to equal 0?
Always. Oh, when
Just at 0.
x is equal
When
to
x
0.
equals 0.
When
Well, then it's undefined.
Then it would be undefined, right?
Also, it's
I
never
guess
gonna
it's
be.
for every, what if it's,
No, it's never gonna be. Whatever,
less,
1/2.
because if it's negative.
Whatever.
it's
It's 2 times 1/2.
No, then it's,
Well, it can't be because
Oh, it's
you need
1.
a negative,
yeah,
big imaginary.
exactly, so it
Yeah.
can't be
So
that,
it
so
can't be undefined.
It will
it
never
would be,
It will never equal 0. Okay? It's never going to equal 0. Think about your parent function for square root of x. It starts at the origin and then starts increasing, right? And it keeps increasing forever. This graph right here
it goes.
is just shifted up 1, right? And it looks like this. Is there ever any peak there?
No, it just keeps going.
No, yeah, it just keeps going. It keeps increasing forever. There's no max point or min point on there.
It's
And we
never
can
equal.
see that because, yeah, it's never going to equal 0. Here it's undefined when x equals 0, right? That's indicative of the fact that we have an endpoint. Okay?
So will there never be a horizontal tangent from radicals?
Not necessarily for any of them with radicals, but if it's just radical x, plus a number, if there are no other x's, like you'd have to look at it if it were like root x plus x or something like
What if it
that.
was like root x minus 5?
Root x minus 5.
Even though.
Like it would be shifted downward.
It'd be shifted down one. Yeah, that one still wouldn't have. It would. All it would be is it would be down here at -5, and it would just start increasing.
Oh, okay.
It'll have an x-intercept. I think that maybe what you're thinking about. It will have an x-intercept, but it still won't have a max or min point.
But even when you set it equal to 0, it's like a red flag. It doesn't look right.
Yeah, if you tried to solve this,
So you wouldn't be able to.
first thing you would have to do is either multiply both sides by 2 root x, or take the reciprocal of both sides.
And in that, it doesn't.
And then you have 2 root x equals 1 over 0, which is undefined. Okay? So, you will have cases like this that just don't work no matter what you do. Okay? There just aren't any of these. Okay? Now, we have a couple of different ones here, and we're going to look at a couple of other examples tomorrow, but I wanted to take a look here at, we have the logarithmic function, okay? The logarithmic function, it says, show that the equation of the tangent to y equals ln of x at the point where y equals -1 is y equals ex minus 2. Notice that's not e to the x, it's e times x. Alright? Now, first thing we want to do is find that point of tangency, or the point of contact. They're telling us they want it to be when y equals a -1. Okay? So, let's think this through. If y is a -1 and -1 equals ln of x, what is x? No?
Negative, it's gonna be -1.
Negative e.
What?
Negative e.
We're getting warmer. This is a log base e, right? So how do you rewrite this as an exponential?
E to
There you go.
Oh,
E
it's
to the
really
-1 equals x. The base to this power equals what's in the log. Okay, so e to the -1. So x is 1 over e. Alright, so that's the point that we're dealing with here. Okay? And we had to get that x coordinate because then now we know how we can get the slope of the tangent at that point. We know what x value we want. What's the derivative that we're dealing with here?
1 over x.
Yeah, it's 1 over x. So that means it's 1 over e, which is e. And look, now we know we got our slope equal to e the way we wanted it to be. Okay?
Yeah, just plug it into the final.
Now you gotta plug it in. Okay? Here's our the slope of the tangent. Here's the point that we want. So y minus a -1 equals e times x minus the x coordinate 1 over e. Okay, so that's y plus 1 equals ex minus 1. So y equals ex minus 2. And that's what we wanted. Okay?
Alright.
So, some kind of cool stuff. Bring back to memory some of the logarithm stuff too. Alright? So, I gave you a little bit of practice. Okay? I weeded out some of the ones that were just repetitive, do the same thing over and over and over again. We did a ton of repetition last unit. I focused a lot more on these problems that are application. okay, and more of the IB level. Alright, so there's only 4 problems for practice, but take your time and, work your way through them, okay?